Right.
Okay, should be ready.
All right. All right, I think we're going to get started here. My name is Kim Busse from the University of Wisconsin-Oshkosh, and I'll be moderating this session on modeling and mapping. Our first speaker is Amanda Grimm from Michigan Tech University, and she's going to be talking about mapping submerged aquatic vegetation in Great Lakes using satellite imagery. So, unless she's not in here.
I'm here.
Oh, you're right there. Duh.
I didn't want to walk right in front of the camera.
You're the star.
So yeah, I'm Amanda Grimm. I've been at the Michigan Tech Research Institute, which focuses on environmental remote sensing for about 4 years. And one of the projects that I've been involved with for the longest time since I've been there is this effort to map Cladophora and other kinds of submerged aquatic vegetation across the Great Lakes. So if you are in this session and have chosen it over other sessions, you probably know something about the Cladophora problem already, but just to set the background a little bit, at a broad scale, Cladophora was a big problem before the 1980s. We would have the problem of big stinky mats of sloughed algae washing up on beaches through the 1970s, and documentation of it being a problem as early as the 1920s. That was one of the drivers for the Great Lakes Water Quality Agreement, and then after that was signed, the problem kind of went away. If you look at the late 80s or the 1990s, you don't really see Cladophora as a problem on the radar, kind of was considered to have been solved. And then the mussels came in. So beginning maybe early 2000s, we saw this great resurgence of Cladophora to a scale even greater than what we had seen in the 1970s, and it was a hot button issue again, especially when it became a large problem in places like Sleeping Bear Dunes that are high priority areas within the basin. So for any kind of environmental problem, one of the main things you need to wrap your arms around it is to be able to quantify the problem. How much algae is there? How much is washing off on the beaches? How much worse is it compared to how much algae we used to have? And that proved to be fairly difficult to do because, beach managers don't have oodles of free time to weigh all of the algae that they're raking up off the beaches. Initially, we looked at using remote sensing imagery to actually measure the amount of algae that was washing up on shores, but that's fairly difficult to do because if you have a two-dimensional image, you can map the extent of these piles of sloughed algae, but you don't really know, is that an inch deep or is it knee deep? Whereas if we actually map the extent of these beds of Cladophora, where they're growing, we can get a much better idea. So what we ended up doing was collaborating with Dr. Marty Auer, who has been working for a very long time specifically on Cladophora, to first map the extent of Cladophora across the nearshore areas of the Great Lakes, and then combine those maps with his... Oh.
The microphone is for webinar, so you just have to speak louder.
Okay. I will speak louder. Sorry. Thanks. So what we ended up doing was map the extent of Cladophora across the Great Lakes Basin in the nearshore zone, and then combine that with Marty Auer's Great Lakes Cladophora productivity model so that we can know where it is, and then use this biophysical model to estimate, if you have a patch of Cladophora and you know where it is, how deep the water is, what the phosphorus and the light penetration is like there, you can estimate the biomass. And with that kind of combination, we can get at, how much Cladophora is growing in the Great Lakes, and then we can backcast using historic satellite data how much used to be growing, how much worse has the problem gotten. So we used the Landsat family of satellites for this program because it's been in the sky for a long time. Landsat satellites are managed by USGS, and they've had at least one active sensor up there since 1975. So that gives us a very long time series of data. We can go back before the mussel invasion, before the Great Lakes Water Quality Agreement, and sort of get at those 3 periods of pre-agreement, and then after agreement, pre-mussels, and then after mussels. So I don't want to get into the nitty-gritty image processing part of it, but basically we use 2 spectral bands from the Landsat satellite images, the blue and green bands, and what we do is look at the ratio between those, because blue light attenuates through the water column at a different rate than green light, and we can use that ratio to correct for differences in water column depth. So basically all of the pixels with the same type of bottom substrate will look the same in this depth corrected index regardless of the depth of the water column that they're in. Excuse me. So the product that we ended up with was circa 2010 basin-wide, apart from Lake Superior, because it's not really a problem in Lake Superior, map of the distribution of submerged aquatic vegetation, mostly Cladophora, but also areas of Chara and other types of benthic submerged algae. Across the lower 4 Great Lakes, the distance that we can go from the shoreline varies depending on bathymetry and water quality. We can see much farther into lakes Huron and Michigan than we can into Ontario and especially Erie. So here's Upper Lake Michigan, where we can see between 12 and 20 meters into the water column. And this is an interactive map, so you can zoom around and zoom in on your area of interest and see what our circa 2010 baseline map looks like for your area. Here's Green Bay. And then Sleeping Bear Dunes area. Sleeping Bear Dunes was one of our focus areas where we spent a lot of time mapping and looking at historic imagery, because there's so much shallow, hard substrate off of these islands and along the shoreline that there's just a lot of Cladophora. And then here's the Milwaukee area. So looking at Lake Michigan in particular, we really saw 2 major areas where there was a lot of growth, the Sleeping Bear Dunes and then this area along Milwaukee and north of Milwaukee. And this is the lake-wide map. So because we use Landsat sensors, they have a pixel resolution of 30 by 30 meters, so that's the resolution of our output map, which works pretty well for the size of typical Cladophora patches, but doesn't go too fine scale. Kind of just said that. So yeah, in Lake Michigan, we see large areas of growth around Sleeping Bear Dunes and Milwaukee, and then sort of smaller concentrations in Green Bay and up at the very north end of the lake. Milwaukee, it seems like a more obvious location where you might expect to see a lot of algae growth, because it's, you know, an urban area and you can potentially have a lot of point runoff sources. We were a little bit more surprised by these other areas where a lot of the watershed isn't necessarily agricultural or urban, but you're still seeing a lot of algae nuisance growth. One of the sort of byproducts of this mapping effort was that looking at these images over time, we could document how much further we could see into the water column as time went on. Back in the 1975 images, across much of Lake Michigan, we could see, you know, 4 or 5 meters into the water column, and that's the deepest water that we could get a reflection back from the lake bottom that was strong enough for the satellite sensor to see. But then moving forward to 2010, we have much clearer water, obviously, as has been documented elsewhere and from field observations. And now I think our average penetration, the maximum mapping depth that we have for this type of nearshore work, is 12 to 15 meters. So there's been a big increase in the amount of nearshore area that we can map. So that sort of, sorry. Now, because we're using satellite imagery and we can only create these maps to a certain water depth, that begs the question of what proportion of the Cladophora we're actually mapping. You know, is there a lot of really deep Cladophora that we're not capturing with this method because we can't see it? So that was the second part of the project where Marty Auer's Great Lakes Cladophora growth model really came in handy, because, you know, we could give it our depth limit and say, you know, here is the conditions that were present at that point in time. Here was the approximate phosphorus concentration and water clarity. What proportion of the biomass of Cladophora would be growing at water deeper than that? And across a lot of different conditions, we generally found that this method was able to classify about 90% of the cladophora growth that the model predicts. So we are missing a bit of deeper cladophora, but only about 10% of our estimated total. So we did this across all 4 of the lower Great Lakes, and the approximate biomass estimates are on the order of tens of thousands of metric tons. So it's quite a bit of carbon being, produced for this nearshore zone in the form of benthic algae every year. Oh. And then adding those 4 lakes together, our total, baseline estimate is about 130,000 metric tons in terms of dry weight. So if you gathered up all of the cladophora in the lower Great Lakes and dried it out, 130,000 metric tons. So in addition to our 2010 map, which was across the entire basin, we were interested in its change over time and whether that varied among regions or across lakes. So we picked 5 different areas where cladophora was historically or currently known to be a nuisance problem. 2 of them in Lake Michigan, and then 1 in each of the other 3 Great Lakes. And at 5-year intervals, we would create cladophora maps from Landsat imagery and look at the change over time. So what we saw at Sleeping Bear Dunes was that we saw a very large increase in water clarity, coinciding with the point in time when Dreissenid mussels invaded that part of the Great Lakes. And associated with that, we saw a big increase in the total amount of bottom substrate that was covered with submerged aquatic vegetation. So we wanted to tease apart in this time series whether we were seeing more cladophora because we could see a larger area or because the cladophora was becoming denser. So we looked at both a standard area, just the very shallow nearshore zone that we could see from 1975 all the way to the present, and then we also looked at the whole area that we could see in each year. So these darker colors, the darker green and darker orange, are those shallow pixels that we could already see in 1975. So you can see that the proportion of those darker pixels that are green that were classified as cladophora stayed about the same. So it wasn't that cladophora was covering more of that shallow zone. It was really that this lighter green area, the cladophora that was now colonizing deeper water, was increasing. So overall, between 1974 and our most recent image in the series, which was 2012, we saw a 4-fold increase in the total area that was clear enough for us to get that bottom reflectance and do a map classification of. And of that, the amount of that area that was classified as SAV increased more than 3-fold. Looking at our other time series hotspot, the shoreline right along Milwaukee and Lake Michigan, we see a slightly different pattern. Again, looking at these blue diamonds, we see a very steady increase in the water clarity at that site, the maximum water depth at which we could map the benthos. And then, unlike in Sleeping Bear Dunes, where we kind of saw the same amount of SAV in that shallow area, at Milwaukee we saw an increase in both the shallow cladophora, the dark green, and the deeper cladophora colonizing those deeper substrates. So both of those contributed to the increase in cladophora at that site. So even within Lake Michigan, maybe an east-west difference at this site. Looking at the overall patterns for all 5 of our hotspots, Milwaukee and Sleeping Bear, as well as western Lake Ontario, the Bruce Peninsula and western Lake Huron, and then eastern Lake Erie, we can look at the pattern of change in submerged aquatic vegetation area relative to a couple of time points that seem really important. So we have those 3 time periods that I spoke about at the beginning, the leftmost being before there were phosphorus controls under the Great Lakes Water Quality Agreement, and then that middle period after phosphorus controls and before the mussel invasion, where for some of these sites we actually see a decrease in cladophora cover, and then right around the approximate time at which Dreissenid became established, large increases at most of these sites in the area of SAV, although there was a lot of variation. Clearly the two Lake Michigan sites showed the biggest change, but kind of the whole range of variation. At the Bruce Peninsula site in Lake Huron, there was actually a slight decrease in cladophora area since the invasion of zebra and quagga mussels. So overall patterns that we see in these time series, we know this from satellite data as well as field data. Water clarity has increased significantly in all four of these lakes to the point where Lake Huron is actually clearer than Lake Superior. The effect of this increase in clarity on benthic vegetation is that the amount of suitable substrate for cladophora has increased by an order of magnitude, which has greatly increased the amount of biomass that we're seeing and the problem of dead sloughed cladophora washing up on lakes. But it varies a lot. Our primary objective was to do this baseline mapping, so we only had the ability to look at a handful of sites, but we saw a huge range of variation among those sites. So obviously there are a lot of strong spatial patterns here, and we're very interested in pursuing further why we see these differences and why this resurgence has been strong in one area and non-existent in another. We also see a lot of discrepancies among the areas where we see concentrated SAV growth. Some of them, like the Ajax-Pickering area in Ontario or the Milwaukee area in Lake Michigan, are along urban shorelines where you might expect higher terrestrial inputs of phosphorus, but others are really in fairly undeveloped areas where you wouldn't necessarily expect nutrient-related problems. So one sort of forward direction that we're thinking about going in with that is that cladophora growth is a local process, but there's sort of a disconnect between the problem and the source of the problem. So you might have sloughed algae washing up on a beach at nuisance levels, but the algae might not be growing offshore of that beach. It might be growing in beds that are miles along the shoreline, depending on the lake circulation patterns. And the algae beds might be miles away from the terrestrial source of phosphorus that's driving that algae growth. So if we compare these maps with hydrodynamic models, that might help us to make those connections between where the algae is washing up on shore and where the phosphorus is actually coming into the lake and driving that local problem. And eventually that could potentially help us prioritize phosphorus reduction efforts. Recently, just within the last year, we've done a couple of smaller update projects since that 2010 baseline map. So we took looks at the cladophora extent in Sleeping Bear in 2010 and 2012 and 2013. And at that site, we're not really seeing a change in the percent of the visible area that's classified as submerged aquatic vegetation. It's hovering right around the mid 30%, but our maximum mapping depth is still increasing. So water clarity is still increasing in this northeastern part of Lake Michigan, and that is leading to further increases in total cladophora. On the other hand, in this western shoreline north of Milwaukee, we're seeing kind of the opposite. Looking at 2010 and 2015, we have very similar maximum mapping depths, so it's not really getting clearer along that shoreline, at least at the two dates that we looked at for those years. But we see a big jump in the percentage of the area that's classified as SAV from around 30% in 2010 to 40% in 2015. So again, differences even within Lake Michigan. In our few years of working on this problem, we've looked at various timescales. At the 2 or 3 year scale, you might see small differences between years that are maybe seasonal in nature. But our time series data really indicates that you see significant changes in the distribution of vegetation at about a 5-year scale. And our baseline map that we finished a couple of years ago was intended to be a circa 2010 map. So now that it's 2015, we'd really like to produce a new baseline map and see how changes are occurring across the basin. So just to sum up, a lot of variation. My primary focus isn't why those variations occur, but the distribution mapping can really help us sort out the differences in whether you see patches in certain areas and not others because of the mussel distribution or onshore or offshore phosphorus. The first step is really knowing where the cladophora is growing. And that's it. I don't know if I have time for questions.
I think just for the sake of time, maybe we'll save them for the end.
Okay.
Unless somebody has.
Thank you.
Tell them to come in. Here's your networking option of meeting 5 new people. Come on up. There's seats in the front.
Just gonna stand on this side. The mic will get you fine. Yep.
So Arbogast, talk with me.
Arbogast? That's okay. How do you say that? So? Okay. Good to go. All right. So moving on, Alan Arbogast from Michigan State University is going to talk about hemispheric ENSO cycling and Lake Michigan coastal dune evolution, a relationship.
A relationship with a big question mark at the end of it.
Oh, question mark.
Yeah. I want to thank everybody for coming. I want to acknowledge my 2 co-authors, Bill Monahan at the Indiana Geological Survey and Bill Lovis, who is in the Department of Anthropology at Michigan State. He's in the audience here. So this presentation is born out of about 6 or 7 years of collaboration amongst the 3 of us, looking at coastal dunes. We're part of a community that's doing that, trying to understand their history, the factors that cause their evolution and force sand to move from one place to another. And this is just kind of an idea that we're sort of kicking around. Now, I cut my teeth working on dunes in the plains. I did my graduate work at Kansas, and I worked on the sand hills and dunes in the central Great Plains, and was lucky enough to get the job up here in '95. And when I started working on the dunes, I was truly blown away by the landscape, no pun intended. It is indeed spectacular. And in my travels and doing some work other places, I learned that they truly are world class. I mean, it's a fantastic landscape. It's right here in the middle of the Midwest, as you guys all know. So the geographer in me wants to know, well, why are these dunes present? We think about where and why and those kinds of questions. And simple stuff, you guys probably already know this, but the western shore of Lake Michigan is where the nicest, best dunes, the largest dunes are. Why is that? Well, of course, predominantly westerly winds, long fetch, clean slate blowing across Lake Michigan, and of course, lots of sand left over from the ice ages. So it's a perfect environment to form great coastal dunes. Now, when I got here in '95, I started looking at these things a little bit and getting into the early literature about this landscape, such as the Geology of Michigan here by Doran Eschman. And at that time, there was sort of an assumption that these dunes had formed more or less in a single continuous event during the Nipissing high stand of ancestral Lake Michigan. And a key thing that was obvious in reading this literature was there were no dates. It was based on sort of an assumption given lake history that was pretty well understood, that about 5,000 years ago there was a high lake phase referred to as the Nipissing, which you may have heard about, and this lake stage would have been when the largest dunes theoretically formed. So perhaps it was right after that lake stage. All of the sand is available from the dropping lakes, and that's when the dunes evolved. And that was sort of a paradigm up here, and I saw it in a lot of different places. Now, I was lucky enough that, I'm at Michigan State, so close by the lake shore, and I started looking in the southeastern corner of Lake Michigan to see, well, what is there that we can learn about these things? And straight away, looking at the stratigraphy of these dunes, you could tell pretty much quick that these things did not form in one single continuous event. This is a photo by Ed Hansen, who's a colleague of mine at Hope College. This is at Van Buren State Park. And if you notice the dark layers that you see in these dunes, those are buried soils. Those soils represent periods of landscape stability as this dune grew. In other words, it did not form at one time. It formed in stages. So right away, that was a source of curiosity for me. Now, most of these soils are little, when we look at soil stratigraphy, are little AC profiles, which means that they were brief periods of stability on the order of maybe 150 to 200 years, something like that. And you can see in these arrows that I've pointed to here, the location within the dune about where these soils would be. So this thing is forming in stages, but brief periods of stability. At the top of these dunes in the southeastern corner, however, there was one very well-developed soil. This is trending towards a spotosol for soil aficionados up here, with a pretty thick A horizon, a well-developed E horizon, which represents some period of leaching in the sediment, and a BS horizon that formed beneath that. Now this soil represents a period of relatively long landscape stability. In other words, when the dune was not growing. Now, in the dunes in the southeastern corner of the lake, you find this soil in the upper part of the profile. So clearly the story was a lot more complex, as we could see in the southeastern corner. This is about the time that I hooked up with the two Bills, who are good friends of mine, and we started looking at dunes up and down the lakeshore a little more broadly, specifically in the northern end of the basin, north of the isostatic hinge line. Now this is the line that represents the place where north of that the landscape is still continuing to rebound, where it might be subsiding slightly in the southern portion of the basin. And if you look at dune systems up north of the hinge line, you can see that they didn't form all at one time either. So the most iconic landscape, of course, is Sleeping Bear, not far away from here. And this landscape is mostly glacial with an aeolian cap on top of that. Work there has shown that winds blowing against the bluff have moved sands to the overlying plateau. Also, dunes in embayments, such as at Petoskey here, seem to have a fairly complex history as well. Looking at this landscape from the air, there are distinct ridges of dunes that indicate some sort of periodic mobilization and accumulation of sand. That seems to be related to the rebound of the landscape and a progressively younger surface being suburbially exposed for sand to accumulate. So the story is more complicated, apparently, than what the old literature was suggesting. So along with several other people, our team started looking at radiocarbonating. Elmer Rawlings in the audience. He's worked on dunes over on the other side of the lake. And what we've done is we've collected a batch of radiocarbon dates from organics within the dunes, in those soils in the dunes. We've also acquired a variety of optical stimulated luminescence dates, OSL, which estimates the last time sand grains were exposed to light. In other words, when the sand was blowing, stopping, and then being buried. So we can talk about how that's done later on. I did not dream that up. There's no way. But it works, it seems to. The two line up pretty well. So here's a representative site. This is from Van Buren again. And what we have at the base of the exposure are lake sediments, theoretically from the Nipissing high stage. Above that, you see the fellow standing there, is a thick organic layer, which is actually an old swamp deposit. So we acquired radiocarbon dates from that. That was a swamp. If you look at the statistics, it was a swamp sometime between 6,000 and 5,000 years ago, maybe for 500 or 600 years, something like that. We don't know exactly. It's about the best we can do. But then the dune began to grow in stages. That swamp was present as the lake was falling likely from the Nipissing stage. At that time, the dune was not present. So the lake falls, sand starts to blow in and buries that swamp. And then the dune grew in stages, and each one of these dates here represents at a high probability when that was buried. Okay? So as you can see, it's growing sequentially through time. This is not a single continuous event that began 5,000 years ago, but one that has gone on since that time. So it's a much more complicated history than was originally thought. At the northern end of the basin, at Torch Bay, which is 20 miles north of here, we have a similar kind of history. Here, the dunes, instead of growing up, are prograding as this younger surface is being isostatically uplifted. And over here on the far right, you can see the Nipissing Terrace, which formed during the Nipissing High Stage. That's between 5,000 and 6,000 years ago. And then the dune sands, are progressively younger as you go towards the lake. So these things are forming over time, not at one time. So we are, we're looking at our stats and we're saying, can we make any sense of this statistically? Throwing all of our dates together, this is the OSL sample batch that we have, 162 of them, and we've created a probability density distribution that looks at the various peaks of probability for when sand was blowing. And as you can see, it begins about 5,000 years ago and has occurred through time. The present is 0 on the right. And there is a significant period of time when there's not much going on. This is what we refer to as the Holland Paleosol interval. That's that thick soil in the southern end of the basin. And it appears to be up and down the lakeshore from the southern end to the northern end, most of the sand is sitting there in place. And so this is, we're thinking, is on the order of 5 to maybe 800 years of stability when very little sand is blowing around up and down the entire lakeshore. So this is pretty cool. And it implies that there are variables going on that must be sort of in concert to make sand blow and dunes grow through time. And we're trying to understand that. So one of the things that we do is we correlate that with the known climate history from that's been reconstructed in a variety of different ways. And we know that there's the medieval warm period, and we see a peak of sand mobilization at that time. Stability before, when it's a little cooler and a little wetter. We look at the lake hydrograph and see how that correlates. And it appears that just looking at these two variables, that dunes have mostly grown during transgressive events as the lake was rising. We're thinking that as the lake's rising, sand is being moved up, it's kind of being shoved up the shore, it blows to form dunes. But it's not always during rising lake levels. There are a couple times where it seems to be best correlated with dropping lake stages, which implies that there's something else going on. Dunes tended to stabilize when lake levels fell. So the energy of the lake shore, something to do with the winds, and timing has a lot to do with when these dunes are growing and stabilizing. Another interesting fact, just to think about, is we've looked at the orientation of parabolic dunes. 1,200 of them. That's what graduate students are for. And I was paying one, and I said, I want you to find all the parabolic dunes. They're like this. I said, I want you to map their orientations, and let's look at them. And the windrows associated with that shows that the majority of those dunes are forming out of winds coming out of the southwest. Now, on Elmo's side of the lake, I bet it's a little bit different. But over on our side of the lake, it's southwesterly winds, which is forming the majority of these dunes, which is pretty interesting. So that must mean that it's big low pressure systems that are coming up out of the plains that are whipping through here, perhaps during the fall months, October, November, when, witches of November and all of that are whipping around, and those southwesterly winds on the front of those systems is what's pushing sand around. That's what it seems to imply. So that means that storminess, it's not just lake level, it's not just the rebound variable, it's not lake dropping, but maybe storminess has something to do with it as well. So what does the recent past tell us? Just in the last 10, 15 years, can we see any interesting patterns there? Well, looking at the lake hydrograph from 96, 97, we all know that in 97 the lake was high, and it had dropped since. It's been bouncing back up a little bit, but there's a very long period of time there, about 10 years, something like that, when the lake was pretty low. Okay? Now, I was lucky. I started looking at these things in the late 90s, after the lake had fallen a little bit. And apparently what had happened was that during that high lake phase, there was a lot of beach erosion, and the guts of these dunes, if you want to put it that way, was exposed. Now, I want to show you what's happened in the last 10 years, last 15 years. This is amazing. Maybe you've seen this yourself. So this is Van Buren State Park in 1999. There it is in 2008. And there it is last summer. So this is one of the few times where I've got an audible wow out of my classes at school. Most of the time they're just kind of looking at me. But at any rate, one lone kid, wow. So the dunes are stabilizing during this low lake phase. Okay? So right away you might think, well, it's the lake stage. The lake's dropped, the dunes are stabilizing. But if we look at just kind of playing around, days with average winds of greater than or equal to 30 knots, it was pretty windy back in the 80s, and then in the early 90s, that's when the lake would have been high, more storms rolling through and whatnot. Winds have dropped, and this is when dunes are stabilizing. So it's not maybe just the lake. It could also be the winds and maybe some local factors that are involved. So the questions we have is, what role do lake level fluctuations play in dune evolution? How do local site conditions matter? And storminess. Well, as we've been thinking about that, we're looking at, well, are there even broader linkages? Just kind of messing around. And it seems like there might be. We've pulled together all the data from Northern European dunes, like those in England that you saw a bit ago. Here are 27 ages from Cape Cod. And look at the period of stability in our dunes relative to Northern Europe and Cape Cod. It seems to be the same. So beyond the local factors, those are marine locations. Those are marine locations. Beyond the local factors, is there something going on hemispherically that transcends both the marine and the fresh? So here's our Dune OSL PDD again, our probability density distribution. And those are periods of dune growth. Okay, the red arrows represent periods of dune stability. There's our Highland interval when the dunes are stable. There's Cape Cod. Matches up pretty good. There is Northern Europe. That matches up pretty good. And just for grins, we took a look at, well, what is, if there's something hemispheric going on here, does ENSO have anything to do with this? Now, I'm not a climatologist. None of us are. But this period of stability that we have during the Highland interval, it also happens to be the time when there was a very high frequency of El Nino as reconstructed from the record in Peru. So, what does that mean? Well, we're in an El Nino year now, right? You hear about that all the time. We know that El Nino are often characterized by mild and warm winters with fewer winter storms. That sounds like stability to me. La Nina years are higher frequency of big systems rolling through, stirring things up. Could that be what's part of the story? We don't know that for sure, but we're starting to wonder. So during the La Nina years, perhaps you have more systems coming out of the plains that are really stirring things up, bringing those southwesterly winds that are driving those dunes. If we are connected with Massachusetts and Northern Europe, then that would imply that there's also some sort of hemispheric thing going on with the jet stream that I don't necessarily know that I'm prepared to describe or talk about, but that there might be some sort of connection that transcends all of this stuff, whether it's marine or fresh. But the common denominator is it's coastal, whether it's here or there. So this is an interesting time because here are our current conditions just from a couple of days ago. I nabbed this off of the web, right? Heard about that big hurricane that came up through Mexico. And, from the Detroit Free Press, maybe a milder winter here and less stormy. If it's less stormy, there's going to be less sand blowing around and that landscape stabilizing. So our message here is that we don't know that we have this all figured out, but it's sort of a tantalizing clue. Is this a smoking gun? We don't know. But it certainly seems to be far more complicated than just what's going on with the lake or just what's going on with the storms. So what that means in the future, I don't know, but it's worth talking about, and it's kind of where we're at right now. We have lots of people to acknowledge. We've had a lot of help from a lot of different folks, both financially and just as far as letting us on their property. And I want to thank you for listening.
All right, I think we'll save the questions for the end.
Yeah, you
We'll
bet.
keep rolling.
Sure. Pop it down and then
We have two of them. So this one, I think I'm just going to open hers right away.
hit full screen. Okay.
So Just a second. Joanna. Bam. Okay. I need my notes. See this right? Fontenelle? Okay. I was right. All right. So this is to just move the slides up. That one's the pointer, and then these two go forward and back. And if you just stand kind of right in this area, there'll be video on you. Okay. We'll hear you there.
All right. So next up, we have a duo, Team EPA something. Samantha Fontenelle and Joanna Mott will be going second. They're going to talk about 6 key steps for developing and using predictive tools at your beach.
Thank you. Good afternoon, everyone. I'm happy to be here today to talk to you about a soon-to-be released guidance, 6 steps for developing and using predictive tools at your beach. I'm joined today by my co-presenter. Can you talk louder for the back? I'll try. I'm joined today by my co-presenter, Dr. Joanna Mott with James Madison University. Dr. Mott assisted us by pilot testing the guidance. She supported the Texas Beach Watch program with the development of 2 models using the guidance, the steps in the guidance. Before I go any further, I'd just like to say the views expressed in this presentation are those of the presenters and not necessarily the views and policies of the U.S. Environmental Protection Agency. So we developed this guidance, which is straightforward and not too technical, to encourage beach managers to investigate whether a predictive tool would be an appropriate and cost-effective addition to a beach monitoring and notification program. The guidance focuses on virtual beach, but is also applicable to other types of predictive tools. And the intended audience for this guidance are local government officials, beach managers, health department personnel, and other stakeholders. So we took a different approach in developing this guidance, different than what we've done in the past. We simply didn't rely on just a review of the literature or what was out there, the best sources that were out there. Instead, we wanted to learn from the beach managers, to hear from them on their experience developing a model and the lessons that they learned. So our approach was to interview modelers and beach managers who had developed a predictive tool, use the information from those interviews as well as information from other key sources to develop the guidance. And once we had a draft version of the guidance, we wanted to pilot test it. And we would do so by asking states to volunteer to develop a model following the guidance, and then provide us with feedback on their process. And then based on that feedback, we would revise the document. So we developed a short list of beach managers we wanted to interview, and that list was based on our knowledge of beach programs we knew were using models, as well as the EPA's 2010 Predictive Tools for Beach Notification Volume 1. And we tried to select models that were geographically diverse, as well as those different types of models. And not surprisingly, most of the models that were being used were in the Great Lakes area. Once we had that list, we contacted state and local beach managers to ask if they were interested in being interviewed. And once we had our volunteers, we sent them a list of questions prior to the interview. And in addition to interviewing those beach managers, there were several other people that we interviewed that had assisted them in the development of their models. And that list included David Rockwell at the University of Michigan, Adam Mednick with the Wisconsin Sea Grant Program, and Dwayne Porter with the University of South Carolina. So our goal with the interview was to find out from the beach managers about their process and the key decisions each one had to make in the development of their model. So we tried to ask them questions in several key areas, starting off with the very general questions like, why did you develop the model? And more specific questions such as data, like what variables did you use and why? Questions about the model development process, like what guidance did you use? What lessons did you learn? What problems did you encounter? We had questions related to cost, like how much did it cost you to develop the model? And questions about public involvement and outreach, like did you seek input from the public prior to developing the model, and then was there outreach post-development? And then questions about the model output as well as validation. So how confident were you in the results, as well as, what were the plans for validating the model? So we interviewed 7 beach managers, and from the interviews we prepared 5 case studies, and the information from all the interviews were incorporated into the guidance. So this is a list of the people that we interviewed. We spoke to Paul B., I won't attempt to pronounce his last name, about the South Shore model, and there were 2 models that were developed for this beach. An impact model back in 1998, and they used that up until 2004, and then developed a nowcast model and started using that in 2005. We spoke to Julie Wood about the Charles River Watershed Association flag model, and this was the only model that was, this model was developed for a water body that has secondary contact recreation. The model predicts the likelihood of exceeding the boating standard for the Lewis and Charles River. And flags are used to warn boaters whether there's an exceedance of E. coli or there's high algae in the water. We spoke to Kathy Brittenbach with the Chicago Park District about several models that were developed for Montrose, Forest, Oak Street, 63rd Street, and Calumet beaches. We spoke to Julie Kinzelman about models that were developed for the North Beach and the Zoo Beach using Virtual Beach 2.0 and 2.2. And then our lone marine model was a stormwater model developed for the Grand Strand beaches of South Carolina, and we spoke to Sean Torrance and Wynn Porter about this model. Some additional folks we interviewed, and their input was incorporated into the model. We spoke to Shannon Briggs, Adam Mednick, David Rockwell, and Dan Ziegler, and David and Adam collaborated with Shannon and Dan in the development of their model. So these are the key takeaways that we got from the interviews, that not all beaches are good candidates for modeling. You might have some wide and unpredictable set of conditions, or it just rarely ever exceeds the beach notification threshold, so it wouldn't be a good candidate for modeling. The importance of data, high quality data for both the development, use, and validation could not be understated. Predictive tools should be fully integrated into the overall beach program, and they could serve as part of a multiple line of evidence in the program. And then the importance of evaluating the model accuracy on a regular basis, and then when necessary, recalibrating in response to changing conditions. And we try to point that out throughout the guidance. And so here are the 6 key steps as outlined in the guidance. Step 1 involves answering 4 key questions. And the first question is there a need for the predictive tool? And the second question is, do your beach have the characteristics that would work with a predictive tool? And do you have sufficient data to develop and test your model? And do you have the appropriate personnel and funding to develop the model and operate and maintain it in the future? So based on your answers to those questions, you would then move on to the additional steps in the guidance. So at this point in time, I will turn it over to Dr. Mott, who will tell us about her experience pilot testing the guidance with Texas Beach Watch program. Thank you.
Should be all set for you. This one. Yeah.
Okay, well, good afternoon. I'm going to be coming from a slightly different part of the country. There's been a lot of Great Lakes. So we came into this project, we were approached, well, Texas was approached because they're one of the states that has not used predictive modeling at all for their beaches. and EPA was interested in encouraging this. And that kind of, I think, came around at the same time as this guidance document being developed. And so what kind of emerged was for this group of us to work as a sort of a pilot study, using the 6 steps and developing a couple of models for Texas and see how well it worked. So there were 4 of us that formed a little team. There was myself, who I'm now at James Madison. It's a little confusing. I spent most of my career in Texas and monitored about 52 Texas sites over 8 years or so, and also had done some earlier work with Texas Beach Watch. So I'm very familiar with Texas. Worked with Richard Hay, a colleague who's a professional geologist. He was the modeling piece of this. A lot of background in modeling, and he's also worked with sanitary surveys at the same Texas beaches. Kyle Snow, who is a graduate student with me in Virginia, who has modeling background but no Texas beach expertise at all. And Craig Davis, who is the Texas General Land Office Beach Watch coordinator. And in Texas, that's where the funding for Beach Watch comes through the General Land Office. So we were asked to assist Tetra Tech with technical support to EPA as part of the developing tools to increase the use of predictive models at coastal, and we were the coastal piece because a lot more work had been already done at Great Lakes beaches. So we were tasked to develop a predictive model or 2, and also to pilot test this guidance document and send back comments, things that we found were useful, not useful, things that weren't addressed, how did it work for us starting from ground zero. So, like I said, we submitted lists of lessons learned, comments, we developed a couple of models. It was a very short project. I was listening to the previous speaker with his 7 years of data, and I'm going, oh, well, okay, we started in mid-June and we had to be finished by the end of September, which was some funding issues. But yeah, so we were on the fast track. So one of the things we did was set up weekly phone calls between Virginia and Texas, and then with EPA and Tetra Tech personnel. Every time if they were available, they came on with us, and we used them extensively for technical support. This didn't work. What happened with Virtual Beach? These kinds of things. So they were very useful in stepping through this. We did have our graduate student visit the beaches so that he saw firsthand what these beaches really kind of looked like, and also gave him a chance to spend a few days with Rick in Texas doing some hands-on with the data management. And then at the end of the project, we met with really our stakeholders, the Beach Watch coordinator and the director of coastal resources, to go through and debrief on what we had found. So we started with step 1, which is to evaluate the appropriateness of a fecal indicator bacteria predictive tool. So this was decision making. Which beaches were we going to use? We focused on the coastal bend part of Texas, which is what it is, right where the coast bends. And that's where I had done monitoring. Rick was very familiar with that area. That's where we were from. So we had 52 beach stations to look at. We went through and answered the four questions in step 1, that they all had lag time, i.e. they're not sampled daily, they're sampled weekly or twice a month in the off season, that we eliminated beaches that had persistent high levels when they did exceed, so ones that would go on being high for 10, 12 days. And then the remaining beaches were prioritized for potential risk, and we confirmed that none of them had changing conditions that might affect the model, which was again a piece out of that first step. All of our beaches had more than 5 years of data. So we narrowed the list to 5, and then with the General Land Office, we selected 2 beaches to focus on. So this is the coastal bend area, and I just wanted to point this out if I have the thing. This is Corpus Christi all along here. This is the Gulf of Mexico. This is Corpus Christi Bay. These are other bays in the Tertiary Bay. We have sampling stations all the way along the downtown bayfront, as well as along the Gulf. and there are other stations that go on up in this area. So I'm really just showing you this because there's a lot of variability in the beaches. We have bay beaches, we have gulf beaches, we have even inland beaches that are all coastal, but they all have a lot of different conditions. And this had been one of the cautions and one of the reasons that Texas hadn't moved to predictive modeling, because they're so diverse. So the two beaches we selected, one of them was along Corpus Christi Bay, and that's McGee Beach, which is shown here on the left. It's in the downtown area, and there are two stations, sampling stations there. The other was Bob Hall Pier, or Bob Hall. There is a pier. It's not a pier like you'd think of in the Northeast with amusements and all this. It's a fishing pier. It's not used extensively. They do have lights now. And then Bob Hall is sort of a stretch of Gulf Beach, and there are actually 8 stations that encompass that Bob Hall Beach. But the results, when you look at the Texas Beach Watch, they're reported by beach, not by station. So, having identified our beaches, we moved on to loading. We were asked to use Virtual Beach 3, and so we loaded the software. We had a couple of glitches. We got those straightened out with EPA. One of the things is that the map has data sources near your beach that you can use. There were no data sources near our beach that we could use. So this was where local knowledge was critical. And so between Rick and Craig and I, we used a variety of sources. We had 37 records for McGee and 36 for Bob Hall in the test set. That was 1 year of data. We had 1,600 records from the National Climate Data Center, had 63,000 from the Texas Coastal Ocean Observation Network. They take data about every 6 minutes, so they had to pass through that, figure out what data to use. We had over 300 records from the Beach Watch program, so that was field observations as well as the bacteria levels. And we also had annual sanitary surveys and field observations from the sampling days. One of the things with the field observations are those days you're taking those observations the day that you're sampling, so they really aren't predictive. So we had a bucket load of initial parameters, and this is just sort of a laundry list of some of the things that we used, but it was, yes, a lot of wind, a lot of temperature, a lot of precipitation, barometric pressure. The last ones are these ones are from the field data sheets, but you can see we used 3, 5, 7 day, we used weighted, we used different ways of addressing wind speed, wind direction, etc. So step 3 was to actually explore the data, and we had a lot of questions at this point. And this was probably where, again, we went back to EPA and Tetra Tech. Some of the things were not in the document that were sort of basic things. You know, what do we do about missing data? How do we deal with these beaches that have more than one station? And we ended up making a synthetic station using the maximum bacteria levels across the beach, because that's how the advisories are done. We used different time periods, and we used weighted data. So, okay, I'm going to be quick. If anybody's interested in the details on the actual modeling, we had 2 people in one thing. Because of the extent of the data, we used R to collate. It was put into Excel, loaded into Virtual Beach. So step 4 was developing and testing the model. The software ran great. We really didn't have a lot of problems other than we would get these error messages and had to keep reloading. For both beaches, the best model we got was a multivariate linear regression model, and both of them included previous day's precipitation, water, and air temperatures. So this was one of the beaches. This was the Gulf Beach. Our R squared was 0.67, but the real casualty, was here. We had 36 samples in our testing year. We had 19 false positives, 1 false negative. This is not something that you're going to take to a beach manager and say, gee, let's use this. For McGee Beach, our R squared was even lower. We had 14 false positives, 8 false negatives. So that was our model. We spent a lot of time developing the model. This was not that was primarily the focus of the whole thing. So steps 5 and 6, which of the 6 steps were not within our scope of work because they address use of the model, and obviously we didn't get to that point. We did have a meeting, as I said, with the General Land Office at the end of the project, and we talked about what we got, where we were at, and a lot of logistics about the diversity of beaches. Could we get to a good enough model? Would we need multiple models? How are we going to run all those models? Overall comments, and this is my last slide, I know I'm over. Virtual Beach worked well with a few glitches, which probably by now have been worked out. The guidance document, we sent quite a few little tweak things to EPA. Overall issues were who's the target user. There were some pieces that were very general, like you've never heard of fecal indicator bacteria. On the other end, there was some very technical information, so it was a little uneven in terms of who was meant to be using this. We wanted to really emphasize the need for people experience in data management. That was the most critical piece, was data management and then evaluating and making decisions on the parameters and what to put in and how to put them in, and weighting and all these other decisions. So for our modeling effort, the challenges were primarily in identification of the data sources, decisions about the parameters, and the data management. And overall, we had too many type 1, type 2 errors to really think that we could use those models to recommend them for either beach. And for that, I'm sorry I was a little long. I want to thank Tetra Tech and EPA for funding, and also a lot of assistance from both Tetra Tech and EPA, as well as the General Land Office. So.
I think we should have got some time.
Like 1 minute. Just my presentation. Do you pull it up? Oh, yeah.
Do you want me to do that while you take a question?
You okay? Sure. No, we're a little behind, so we can. Yep. Line up again, Shannon. I just want to do my acknowledgements. Where's yours?
Mednick.
Fontenelle. Fontenelle. Where's that? I think it's still up. That one. Okay, it might still pop up there. Okay, down. Okay. This one or this one? Yeah, both of those. Okay.
So I'd just like to acknowledge and thank all the folks involved in the interview process, as well as in the development of the guidance. That list includes Julie Kinzelman, Diane Ziegler, Julie Wood, Paul B., Sean Torrens, Kathy Brittenbach, Shannon Briggs, Stephan Curtis, David Rockwell, Adam Mednick, Joanna Mott, Craig Davis, Richard Hay, Kyle Snow, and Shannon Prendergast and Jonathan Simpson from Tetra Tech. Thank you.
Thanks.
Thanks, Adam.
Thanks.
All right.
Oops, sorry.
Here you go, Adam. So next up is the infamous Adam Mednick from UWC grant. He's going to discuss implementing predictive models, practical advice, and new tools.
So I tried last speaker. Thank you for staying around. Anyone who's still online, please stick around for a few more minutes. I tried to be true to the title of this, except I'm going to talk about tools first and then practical advice. I think it dovetails nicely off of the last two presentations. So real quick background. This map shows kind of where the hot spots are. Those are counties around the Great Lakes and what the percent of exceedances of the old action value, the 235. And then you kind of see the different frequencies of testing. So this is kind of like, where we're, the domain that we're working in. And then just kind of our dirty little secret, what the problem is, we issue advisories on the wrong day. And so if you look at the red columns, that shows on a state by state, both on the advisory side and on the open side, where we have data, how frequently those data were. The data are not wrong. Just want to make that clear. The samples are good, mostly. It's just they're applied to the wrong day because of the timeline. So we all know that. We've been talking about that forever. Here's the totals. So about 2/3 of the closures and advisories were on the wrong day. And while it's only about 10% on the open side, there's a lot more open days. And so, there's about 4,500 that we know, looking backward over those 3 years, like maybe not healthy for people to be in the water. And then you see about a 20% error rate overall. So that was the problem. And then, lest I forget, so this is a screen cap of Virtual Beach, the 1.0, the ancient version, which some of you might recognize. And so I don't forget, kind of the father of Virtual Beach, the person whose idea it was, and sort of foresight was Walter Frick, who's a retired oceanographer at the EPA Ecosystem Research Division in Athens, Georgia. And they've had since then a long team of very talented people working on this. But this is what it looked like when I kind of got on the scene in 2009. And I don't know what the point of this image is, but I saw this when it came out in July, and I thought, I got to put this into the beach conference thing. So, and I'm trying to think of what the tie-in, I guess, back in 2009, the idea of implementing Virtual Beach was kind of a virtual reality. It wasn't real. We talked about it, but it wasn't really happening. So how that changed, you kind of get a sense here where and when it changed. And I forgot to ask, can I get a show of hands how many people are local officials here? County, regional? Actually, not that many. Anybody from outside the Great Lakes besides the Texas presenter before me? So, okay, well, sorry. If you're outside the Great Lakes, it's not quite as easy for you as you saw in the last talk. But if you're inside the Great Lakes, it's not all that hard. And 2011, 12, 13 is kind of where GLRI kicked in. So there was a lot of work that was funded, a lot of modeling implementation, work that was funded through GLRI. And those little boxes are kind of representing, I'll just point out what we're talking about here are communities, not beaches. Just remember, beaches don't make decisions. So we like to count beaches. I've got 100 beaches, but it's really how many jurisdictions are implementing it. So we're around 30 around the Great Lakes, local jurisdictions. Those little boxes are case studies that I did for my dissertation a little while back. And I put these quotes up just for those of us who are not local officials, just to remember that there are different motivations, there are different concerns. You can't go into it as an applied research and development person and say, like, I know everybody wants the same thing. They were sort of different. And these people kind of came at it from different places and at different times. I just like the last quote. He or she says, I went to my administration and said, there's some guy from Madison, which is me, who's really pushing Virtual Beach, and I've heard that such and such other community is using it, and that was their way in. It wasn't like a lot of, different people have different motivation. We'll just leave it at that. So you've heard of ahead of the curve, behind the curve. This is kind of that you can apply this to iPhones or laptops or whatever. This is how it goes. Unless something just doesn't work and people say forget it and they move on to the next thing. So there's in this literature on diffusion of innovation, and it's just, they go back to like shipbuilding. It always looks like this. The question is, are we at this sort of takeoff point where, we got past like the people who are willing to take the first shot at it, deal with the glitches that were referred to, whatever, and then it gets to a point where it just kind of takes a life of its own. I don't know if we're there yet, but that's kind of the hope at least, but there's still barriers. So this was a survey that was that I helped to conduct with David Rockwell and some other colleagues. There's a NOAA technical report out on it, and this is just telling you what the local health department people already know, which is that people don't spend a lot of time on beaches in general. It's amazing how much people care about and come to these conferences, and then you ask, well, how much time do you spend? It's like none. Coming to this conference apparently is half of it. So you can see like that 38% about summer interns conducting more than half of their beach-related work. That's actually a subset. Those are of local health departments that are responsible for more than 5 beaches. So these are ones with a lot of beaches, and most of that work is in a lot of cases being done by seasonal staff. Limited know-how, that's a barrier. Doesn't really tease out that well from this survey, but it certainly does from interviews and just from our experience. You just hear people say like, oh, it's very technical. I don't understand it. It's just like kind of scary. So, the way that came through, at least in this survey, is, we offered up different options for information sources or tools, and sort of, or actually this was training. Folks really wanted to, it wasn't number one. I think number one had to do with source tracking, but learning how to use Virtual Beach was sort of in demand when we asked people. This was a survey of basically of all the quote-unquote beach managers on the Great Lakes, and we had a really good response rate, so these data are pretty good. Then we had 86% on two things which are interesting in terms of data and tools. The questions were, what kind of information resource would you like? And everybody says, we want data. We want free data. Give us data. So that was very high. And then predictive modeling tools. So now I'm going to move from barriers. And actually, so this was just like the one thing to take away from this talk is just this website. SeaGrant.Wisc.edu/Virtual Beach. We kind of officially launched it on Labor Day, which was kind of silly because the summer was over. But if you just Google Virtual Beach, you'll get there. And there's a lot of stuff here you can kind of tune out now. You don't have to listen to me anymore. You can just go there when I'm done. Virtual Beach 3.05. So these are the new tools. So one new advance is this sort of it's a different modeling method, and basically the takeaway is that it's easier and faster. And I think for most people that's what they want to know. It's a non-empirical model, but it's something that cuts the process down, from maybe a couple days to a couple hours. So that's helpful. There's training on that and videos on the website. I'll get to that later. Also, a direct connection to something called ENDAT, Environmental Data Discovery and Transformation. It's a web portal. So this is kind of an answer to the we want web-based data. So it's online data on things that go into these models. And this is where, if you're in the Great Lakes, you're golden. If you're not in the Great Lakes, you're not so much, because at least at present, it's Great Lakes specific. So data on rain, river discharge, clouds, waves, currents, all kinds of things that go into your models. There are other things that you could use and should use for your models. I'll get into that later. But any beach, so wherever you are on the Great Lakes, you can tap into these data. This is what on Virtual Beach 3 Plus, the GBM looks like. I'm not going to get into, just spare you the details of the science of that. The traditional MLR modeling, the part I want to stress, is that's still there. It didn't go away, and there are good reasons to do both. Again, if you want to learn more about it, I would encourage you to take a closer look at the website. But they're very nice tools, and there are some glitches. We're constantly, bug fixing them and so forth. But in general, it's come a long way from what was available back in 2009, 2010. It's really about optimizing and sort of efficiency. And now that we have all of these data that are easily integrated with it, it becomes kind of a big data process now. And downloading the data from ENDAT. So what is ENDAT? Oh, so it's kind of a screen cap. So these are some of what it looks like when you beam into ENDAT and it comes into Virtual Beach. If anybody's used it, there's like a prediction tab, and you make predictions based on the different parameters that you're using to predict E. coli with, or Donna, or cyanobacteria, or whatever else you want to predict. So this is like rainfall 48 hours, rainfall 120 hours, air temp, cloud comfort. So with this ENDAT, it kind of goes on and on and on. You can get dozens of different variables, and you can crank them through these big data optimizations, and you can come up with a model. This is like the front door of ENDAT. You don't necessarily need to go there, but this just shows kind of the way to think of ENDAT is virtual buoys. So these are their radar rainfall. So like if you see the map of the radar rain, well, behind all those pixels is an estimate of rainfall. So that's what the little red circles are. The squares are river gauges. The blue dots are all manner of hydrodynamic data, waves. They're not data, they're interpolations from systems that NOAA developed and implemented. The Great Lakes Observing System, or GLOSS, is very involved in this, and of course USGS is an important partner. There's online training, so people wanted some training, so I'm on YouTube, which I'm not necessarily happy about, but you can't go to YouTube and type in virtual. I don't think don't type in virtual beach. I don't know what'll come up, but maybe not something we want to go over. You get at this through the Virtual Beach website. Users group. So Shannon was talking about how the QPCR that's going on in Michigan, and whoever wants to be involved, and I signed up for that list. There's a QPCR listserv, and so we have one for Virtual Beach. Again, go to the website, sign up, get on the list. We've had, it hasn't been that robust, the users group yet, but it's coming. We have some deliverables or some products coming out of that in the next few months, which I'll close on. But we did convene, and I've communicated with a number of Virtual Beach users in kind of an ad hoc manner, and the website and what's on it really came out of that. And one thing, just for an example, that people said they wanted was, geez, these Virtual Beach files that you create are huge, and I can't email them to the person at MSU or whoever that I might be working with. So just if you want to get a free file share thing and be a part of that, it's password protected, but you and your colleagues can beam these large files to each other. Okay, so where I'm going to close is on best practices. So this is kind of the dovetail with Samantha's talk. So we don't have any document now, and it's a little bit more organic, I guess, and it's coming out of a project that I'm working on now, which finishes in March. That's why I'm saying in March there will be a document of best practices, but I didn't want to not give the practical advice, so I'm just going to give it, even though this is not sanctioned by anyone except for me. So model operation, best practice, daily. So one thing I didn't mention about Virtual Beach 3 and NDAT, and so there's new modeling tools and these new online data means that you can make predictions every day, including days that you don't go into the field. So that means, however often you have somebody who can download the data and run the model, you can get a prediction. The way we like to do it, and it'll probably be a best practice, is two-tiered. You do kind of a traditional field-based model, field/NDAT, big data crunch model on the days when somebody's out in the field collecting a sample and doing your routine sanitary survey. All other days you do this kind of kitchen sink data crunch, and you do it daily. Time of day is important at this point because I don't want to go into the details so much, but basically those online data only refresh so often. If you go towards like noon, first off, if you go late in the day, it's irrelevant to your beachgoers. Second of all, it just stay early. Operating in conjunction with regular data reporting. This is like if you're a local health department, what the example I have is where different people are doing different things, and it could be one person. So somebody might be entering the data, running the model, and then emailing the results to somebody else who enters the data into the website that goes to EPA. It works better if you just streamline the whole thing. It only takes about 10 minutes, and you kind of avoid human error and confusion. So it's efficiency. And I think one of your, one of Samantha's guidance document findings is you got to fit this into the regular process that the locals are working in. Please report model as the reason for a beach action. If you don't do that, if you run a model and then you forget to say that it was model, we don't have a good way of capturing the benefit of using the model, and that's something we're sort of talking about. That's a best practice. Here's the minimum field data, and this is already now required in the Beach Act contracts in Wisconsin. We're saying have to collect these things. Don't stop collecting these things, even if they don't go in your model from one year, they might go in another. These are all routine sanitary survey things. They're easy to do. Collect them. Turbidity is an optional. Like, not everybody has a turbidity meter. So the clarity categories, for those of you who are in the beach monitoring world, that's like, is the water clear today? Is it somewhat clear, turbid, etc.? If you can do more, that's great, but don't stop doing something. Because if you then go back and need those data to refine your model and you stop collecting it, you've just lost 20 data points. So that's important. Sampling frequency, apologies to Michigan, 2 times a week is really minimum. Is the minimum to have enough data points to, have a valid and to be able to validate and have a good calibrated model. 3 would be better. A lot of the impetus for using Virtual Beach is to reduce the frequency of sampling because that saves some time and money. I don't think you want to go 2. 1, I haven't tried it. I mean, Donna, you did the cyanobacteria with like 30 data points, so maybe 1, but I'm not sure. I think more is better. Validation metrics. Virtual Beach gives you some metrics to tell you how you're doing. I think I only have about 10 seconds left, so I will say that in terms of how frequently you validate, and by validate I mean check in a more rigorous way of how the model is performing, that 50%, it's just basically saying the model predicts at least half of the exceedances, and then at the same time, not more than 10% of errors on the other side. That's kind of, that comes out of a lot of USGS work. That's just kind of a rule of thumb, and it's a good one. So if you're looking at that, don't look at that every week. Don't get obsessive about how's it doing this week or this day. There's a certain confidence you have to have, I think, in maintaining this, not looking at it every second and like, oh, it missed it today. Because when you report that it was model and we're able to look at the data, we find always, everywhere, with very limited exceptions, that you do better than not using the model. So you might miss it some days, but you don't want to just stop using it. However, you do have to keep the model fresh. So, you can think of it as recalibration. We call it model building. The preference is that you do it every year in the off season. You incorporate the new data from last summer. We have places that kind of rest on their laurels and go for a couple, 3 years. We're starting to find that after 2 years, you're risking it. And maybe, we're going back to, say, you do kind of a midsummer check and you find out it's not doing too well and it's a 3-year-old model, maybe, now's the time to recalibrate. Reasons for overriding predictions. This is where I get up on my soapbox. I don't care if you're doing models or qPCR or whatever. If you should always check the Weather Service dangerous current forecasts, and if it's dangerous for people to swim, please consider that. Point is that the models are not telling you what to do; they're suggesting what to do. So you can use your best professional judgment, and then if the model cannot be run, just go back to the old way of doing it. So sometimes NDAC goes down, or somebody's sick. This is kind of, and again, these are not official, but these are the practical tips that I can provide now, and I'm done. Website.
Speakers want to come up here and we can ask some questions. We got about 7 or 8 minutes for questions, if anybody has any. In the back.
You said that you could get data from those species around the Great Lakes. Does that include Ontario?
The question was if you can get data from Ontario. Is that for?
Lake Ontario or Canada?
Canada.
Yeah, so the only thing you can't get through NDAT in Canada right now is tributary gauges. However, that should be available through a project with Great Lakes Observing System, and Environment Canada is supposed to be a partner on that. So in about, maybe the summer after next summer, everything else, all the currents, all the weather data are available in Canada.
Donna.
So Joanna,
Yeah.
I wanted to tell you not to give up. That you only had 2 years of data, and you might not have had a lot of data, and you might have missed some important.
We had more than that. We went by the guidance which suggested 2 years of training and 1 year of testing, and so that's what we used.
Okay, but sometimes it takes a little longer.
I agree. And if
So don't give up. But the other thing I wanted to say is probably you have a pretty long recreation season, longer than we do. So you may want to consider that you use a different model in the spring than you do in that hot summer. And that might be where you're kind of missing it. And have you looked at that at all?
No.
No, okay.
We did talk about what's part of the year to use and whether to use all the data, and the issues about less data from some parts of the year than other parts of the year, because February, there's no sampling in February, and recently there hasn't been in December either, just because of cost.
Okay. But it's still warm enough to swim in February.
Not very many
Not
people
really.
swim in February.
Okay.
But yes, okay.
Something to consider.
Only
But don't give up.
northerners. Only northerners.
Yes, yeah, pretty much, it's, you know.
Amanda, you mentioned Milwaukee for that for a problem associating it to the urban setting. Is that, can that be attributed to the combined sewer system in Milwaukee? Is that, I don't know how unique that is to Milwaukee. I think it's pretty unique.
I don't really know. I mean, the nutrient part of the Cladophora equation isn't really what we focus on. We're really just the mappers. So we kind of just looked at the macro scale at where our hot spots were, and in general, whether those were near urban or agricultural or undeveloped areas, and looking for patterns, and didn't really, they seem to happen.
Urban areas that are notably absent from the lack of
I mean, for a Cladophora hotspot, you really need phosphorus availability and water clarity that gives the light penetration you need, and substrate. So I think it's pretty substrate dependent. If you have cities that are along parts of the shoreline with muddy or sandy substrates where you don't really have a lot of hard substrates for Cladophora to grow, you're not going to have a big issue there.
Any other questions?
Is Virtual Beach on the oceans? Why aren't you guys looking at tides?
The question was, with Virtual Beach, why aren't we considering tides? Who wants that one?
That's a really good I don't know anything about the marine environment. I will say that a lot of the kinds of hydrodynamic models that we have in the Great Lakes are actually in the process of being upgraded to sort of like a different kind of model, higher resolution, better, and simultaneously there are efforts in different marine environments to do the same thing. And so the hope is that in the future they will flow into this NDAT system just the same as the Great Lakes. So that may be a couple, 3 years off, and I don't know if Texas is part of that, but tides would be an obvious parameter to put in that data system. And then you could run it through the model and see what the impact is.
Yep.
I honestly have never thought about sand dunes in my life. And
Welcome to the club.
the sand dunes are building up over time. Where's the sand coming from?
Well,
let me just. The question was about where the sand dunes are coming from.
how far back in time do you want to go?
But it's kind of like they're growing slowly over time, so the sand is blowing from somewhere.
Yeah, sure.
From the other side of the lake
You know,
to this side of the lake?
No, it's in the end, it's all Canadian. Rock, it's been reworked by ice from the Canadian Shield. And some of that sand would have been exposed in bluffs that was eroded, slid into the water, then is reworked by waves and longshore current, moved down the beach. It's nudged up onto the beach that way and then blows up to form dunes.
We don't have to give it back, do we?
Don't have to give it back, no.
I think we have time for one more. Yep.
Alan, you mentioned the geology of Michigan, or Michigan geology, the older book. How relevant is the section on sand dunes now?
How relevant?
The question was about the relevancy of the. Sorry, say it again.
Michigan geology.
Michigan geology. There you go.
That's a good question. Certainly in a descriptive sense, it's relevant. In terms of the discussion of age and how old the dunes are, what processes form them, how closely tied in time with glaciation, it sort of loses its relevance there. They don't spend a whole lot of time in the book, quite frankly, talking about dunes. So it's sort of brief relative to the other things. So I don't know if I'm answering your question, but, you know, I don't want to knock it, but as far as age, it's not particularly relevant.
Well, I think that's all the time we have, but I'm sure you guys maybe be willing, if there's any additional questions, and thank you for coming.
All right, come back tomorrow, 8:30.
8:30.
Look for food and drinks. Are there going to be breakfast tomorrow?
Yeah, I think
All right, snacks and coffee tomorrow, but be back here at 8:30.
Starting at 7:30.
Well, I guess
Yes, and